In this video we're going to be looking at intermolecular forces, and these are sometimes called secondary bonding. So these forces are the forces between molecules. They are relatively weak and they affect the physical properties of a molecule, such as its melting points and boiling points, and therefore its state at room temperature. There are three different types of intermolecular forces, which are often collectively called van der Waals forces after the scientist who discovered them. And they are dipole-dipole forces, hydrogen bonding, and dispersion forces. Now, dipole-dipole forces occur between polar molecules. For an example is hydrogen chloride molecule. Now, the hydrogen chloride molecule is a linear molecule which is polar. Now, it's polar because the chlorine atom is more electronegative than the hydrogen, and this results in a permanent dipole being created, and that's represented by these symbols. Now, this is a partial negative and a partial positive. So if you've got a molecule with a partial negative and a partial positive charge, it will be attracted to another molecule. So that partial negative will be attracted to the partial positive of a neighbouring molecule. So, and vice versa. So this partial positive here is attracted to the partial negative of another molecule. Now, this is called a dipole-dipole force. Now, that dipole-dipole force means that the melting point and boiling point of a hydrogen chloride molecule would be higher than something of similar mass. So, the stronger the dipole-dipole forces, the higher the melting points and boiling points. This can be seen with methanol and ethane. Methanol has a molecular mass of approximately 30, and so does ethane have a molecular mass of approximately 30. Methanol is a polar molecule and ethane is a non-polar molecule. Methanol's boiling point is -19 degrees Celsius, whereas ethane's boiling point is equal to -88.5 degrees Celsius. So methanol, with its polar molecule, creates a permanent dipole between the carbon and the oxygen. This can create a dipole-dipole force between other partial negatives and partial positives, and this gives it a much higher boiling point than something like ethane, which is of similar mass. Hydrogen bonding is a special type of dipole-dipole interaction. They've separated it into its own group because it's approximately 10 times stronger than a dipole-dipole interaction. Now, for a hydrogen bond to occur, two criteria must be met. Hydrogen must covalently bond to a freak of nature, and these are the three most electronegative elements of the periodic table. The hydrogen atom of one molecule then forms a bond, which is the hydrogen bond, with the lone pair of electrons of the freaks of nature of a neighbouring molecule. For example, if you had HF, hydrogen fluoride, the hydrogen here forms an attraction with the lone pairs of electrons on a neighbouring molecule. So there is the hydrogen bond. Now, this bond is particularly stronger than a dipole-dipole interaction, and this is because hydrogen only has one electron, and when it's bonded to a freak of nature, these elements are so electronegative that it pulls that one electron extremely close to those atoms. This leaves an unusually bare nucleus, which creates a superdipole. That superdipole forms an interaction with the lone pair of electrons on a neighbouring molecule, which is the freaks of nature, fluorine, oxygen, nitrogen, and that creates an unusually strong interaction. So that can happen, for example, with hydrogen fluoride. Ammonia is another example. So in this particular case, there's the lone pair of electrons, so that's negative. These are all positive, leaving an unusually bare nucleus, which gives it a superdipole. And the hydrogen bond occurs between the lone pair of electrons on this molecule and the hydrogen of the neighbouring molecule. Further example is water. Got two pairs of lone pairs of electrons. Don't forget to put your dipoles on. And the hydrogen of this molecule can form a hydrogen bond with the lone pair of electrons on the neighbouring molecule. To get an idea of the strength of the hydrogen bond, let's have a look at a comparison between methanol, methanol and ethane. All of these have a molecular mass of approximately 30. Methanol's a little bit higher at about 32. Methanol is a polar molecule and it has dipole-dipole forces. So if you look at methanol, remember, it creates a dipole-dipole interaction. Don't forget to put on your dipoles. And that raises its boiling point to -19 degrees Celsius. Ethane, being a non-polar molecule, doesn't have these type of interactions. Its boiling point is -88.5 degrees Celsius. Methanol, though, has a hydrogen which is covalently bonded to a freak of nature. This makes it a polar molecule and it contains some hydrogen bonding. Remember, the hydrogen bonding creates an unusually strong interaction. So make sure you put your dipoles on. So here we have a situation where that is negative and that's positive. It creates the hydrogen bond, remember, with the hydrogen of one molecule and the lone pair of electrons with another. This gives it an unusually strong interaction and its boiling point is 64.7 degrees Celsius. We know there must be some sort of force between nonpolar substances and even atoms such as noble gases, because they can be converted into liquids and solids. Now, those forces are caused by the creation of temporary or instantaneous dipoles, and this is due to the movement of electrons. So at any point in time, if you had a non-polar substance, for a moment in time, due to the electrons being closer to one end of the molecule than the other, this creates an instantaneous dipole. This instantaneous dipole can induce an instantaneous dipole in a neighbouring molecule. and this would be called a dispersion forces. Now, we know that every substance has electrons. That means every substance has dispersion forces, but they're not always significant. This is the only force between non-polar molecules. And what we've found is that the dispersion forces increase with increasing mass. So if you look at this example, these are all non-polar molecules. The molecular mass, you can see, is going up. As your molecular mass increases, so does the number of electrons. And these electrons are getting further and further from the nucleus. Because they're getting further from the nucleus, these molecules down the bottom here are more polarizable. What that means is it becomes easier to induce a temporary dipole. And that's because the nucleus doesn't have as strong a hold as they get larger. Now, because it's easier to induce temporary dipoles, what you can see happening here is the boiling point goes up. Now, another example here is with some more polar molecules. In this particular example, we're looking at the hydrides. This here is a very polar molecule. In fact, it creates a superdipole. So this one here has got hydrogen bonding as its main intermolecular force. It also has dipole-dipole and dispersion. You can see it has quite a high boiling point, and that's due to the hydrogen bonding being present. When you get to hydrogen chloride though, chlorine is less electronegative. So it's no longer creating a superdipole, but it's still a polar molecule. You can see here, this one's got 18 electrons. Its main intermolecular force is dipole-dipole interactions, but it's also got some dispersion forces. And its boiling point is negative 85.1. What a difference that hydrogen bond made. When you get to hydrogen bromide, however, it's still a polar molecule, but bromine is much less electronegative than chlorine. So the polarity of the molecule has decreased. So what we're seeing here as we go down the periodic table is the polarity of the molecules is decreasing. It, however, has a larger molecular mass, which means it's got a lot more electrons. Because it's got a lot more electrons, it's now more polarizable, and its dispersion forces are much stronger, which is why its boiling point has actually increased to negative 66.8 degrees Celsius. Once you get to hydrogen iodide, it's still considered to be a polar molecule, but it's not very polar at all, because the electronegativity of the iodine is much less. But look at its molecular mass. It's huge. It's 127.9. It's got a lot more electrons. Those electrons are further from the nucleus, making it more polarizable. Because it's more polarizable, its dispersion forces are much greater. So therefore, its boiling point has increased significantly. When looking at melting and boiling points, you must consider the total intermolecular forces, and substances are only comparable if they have similar formula masses. So for example, if you look at water, water has a formula mass of approximately 18. It's a polar molecule, and its total intermolecular forces include hydrogen bonding, dipole-dipole, and dispersion forces. Its boiling point is 100 degrees Celsius. If you look at methanol, its formula mass is approximately 30. It has dipole-dipole interactions and dispersion forces, but its boiling point is negative 19 degrees Celsius. If you look at iodine, its formula mass is approximately 254. It only has dispersion forces, but its boiling point is 184 degrees Celsius. So none of these are comparable because they all have different size formula masses. You certainly cannot compare a tiny little water molecule, which is like an apple, to a massive iodine molecule, which is like a watermelon. So you can only compare things directly if they have similar formula masses. I'd like you to try some yourself, so go to the OneNote, intermolecular forces again, and look at shape, polarity and intermolecular force worksheet and try some problems.